Okay, so today we are going to study acid-base indicators. So what are indicators? So these indicators are used in the titration to check the endpoint. So what are indicators? Indicators are weak acid or weak base which show different colors. Weak base which shows different color in their dissociated and undissociated form. In their dissociated and undissociated form. So what does it mean? Let us see that if HIN is our indicator, this is a weak acid, it will dissociate into H plus concentration and IN negative concentration, IN negative ion. So HIN shows color 1 while IN negative shows color 2. So if I write the equilibrium constant for this acid, this will be concentration H plus ion multiplied by concentration IN negative and divided by the concentration of HIN. Okay, so this is the equilibrium constant for this acid. Suppose the pH of the solution is greater than pKa, that means pKa of this HIN indicator. So when pH is more, it means that H plus ion concentration is less. So H plus ion concentration is low, it means that we have less of the H plus ion in this solution. So the reaction will move forward. So the above reaction will move forward. Reaction will move forward and therefore we will have more of the IN negative ions in the solution, and therefore the concentration of IN negative increase and HIN will dissociate. So therefore it will show color 2. So if pH is greater than pKa, we will see color 2, and if pH is less than pKa, so pH is low, it means that H plus ion concentration is high. So if the H plus ion concentration is high in this reaction, so the reaction will move backward. This equilibrium will move backward. Reaction will move backward. So if reaction move backward, it means that the concentration of IN negative will reduce and the concentration of HIN will increase. So if the concentration of HIN increase, we will see color 1. So based on the pH, this indicator show color 1 or color 2. So the pKa of this indicator is very important. So where it is used? It is used in the titration. So in the titration we choose an indicator. So suppose this is my titration curve and we choose the indicator whose pKa, where it changes the color, lies in this region. So the pH of the indicator, pKa of the indicator should lie in this region. So that is a perfect indicator for this titration. So the indicators, acid-base indicators, are given in your data booklet. You can check the data booklet to find several indicators, acid-base indicators, and their pKa values. pKa values, the range of the pKa values in which they change the color. So that pKa range should lie within this vertical line pH, this pH for this titration curve. Okay, so now we study the universal indicators. So what are universal indicators? Universal indicators. So actually universal indicators are mixture of many indicators with a wide pH range of color change. So they have a wide pH range in which they changes their color. So they are mixture of indicators, mixture of indicators. So universal indicators are mixture of indicators. Mixture means many indicators are there with a wide pH range of color change. Mixture of indicators with a wide pH range of color change. Okay, so now we will study buffers. So what are buffers? Buffers are the solutions which resist the pH change. That is, when a small amount of acid or base is added to them, they resist the change in the pH. So buffers are the solutions which resist change in pH when a small amount of acid or base is added to them. So you should note that we are adding very small or the small amount of acid or base, then the solution will resist the change in the pH. But if we add large amount of acid and base, then they cannot resist the change in pH. They cannot keep the pH same. So what are the examples? What are the examples of buffers? So first buffer, it is a combination of weak acid and its salt with strong base. Weak acid and salt with a strong base. Example like ethanoic acid, which is also known as acetic acid, plus its salt with strong base like sodium acetate. So it's a salt of ethanoic acid with a strong base. So if we mix acetic acid and equal amounts of sodium acetate, we will get a acidic buffer. So this is my acidic buffer. The pH of this buffer is in the acidic range, that is pH greater than less than 7. Second, we can make buffer by mixing weak base and its salt with strong acid. Example, weak base, ammonium hydroxide and its salt with strong acid like ammonium chloride. So this is my basic buffer. So this buffer has a pH greater than 7 and it will resist the change in pH when a small amount of acid or a base is added to them. Third buffer we can also make by weak base and salt with weak acid and its salt with weak acid. For example, weak base, ammonium hydroxide, and salt with weak acid, ammonium acetate. This is also a buffer. This is a buffer of weak base and salt with weak acid. We also have buffer with weak acid and its salt with weak base. For example, acetic acid and its salt with weak base, ammonium acetate. So these are buffers. So now we will study how the buffer works. So let us take an example of uh, buffer of weak acid and it's salt with a strong base. So this is my weak acid and it's salt with strong base, sodium acetate. So we mix equal amounts of acetic acid and sodium acetate, we will get an acidic buffer. Now how do this buffer works? So we know that acetic acid is a weak acid, so it will partially dissociate into acetate ion and H plus ion. Now sodium acetate is a salt of this weak acid with strong base. It will dissociate to give CH3CO negative and sodium ion. Now let us assume that we are adding some acid to this solution. Acid means we are adding H plus ion to this solution. Add some H plus ion means the acid to the solution. So what will happen? The concentration of H plus ion will increase because we are adding acid. So in equation 1, the H plus ion concentration will increase. So according to Le Chatelier principle, the reaction will move backward because H plus ion increased. So this H plus ion will react with acetate ion and it will form acetic acid. So reaction 1 will move backward and H plus ion combines with acetate ion and H plus ion will be consumed in this buffer. So the pH will not change, pH remains the same. And where will this acetate ion come from? Acetate ion will come from equation number 2 because equation number 2 is giving us acetate ion. So you keep on adding H plus ion. So this acetate ion from equation number 2 will react with H plus ion and they will form acetic acid. So H plus ions will keep on consuming and the pH of the solution remains the same. But if you add large amount of H plus ion, then all the acetate ion will be consumed and they will react with H plus ion and form the acetic acid, and then when there will be no more acetate ion, then the pH of the buffer will increase. So there is a limit to which the buffer can resist the change in the pH. So therefore we always say that we add small amount of acid, then only the buffer can resist the pH change. Now let us see, suppose we add a small amount of base. So base means we are adding OH negative ion. So what will happen if we add OH negative ion? So the OH negative ion will react with H plus ion and they will form water. So this H plus ion will be consumed in equation 1 and therefore the reaction 1 will move. Therefore reaction 1 will move forward. So reaction 1 will move forward and our OH negative ions will be consumed and they will react, means they will react with H plus ion and will be consumed. So the pH of the solution won't change. But if we add large amount of OH negative ions in the solution, then all the acetic acid will be dissociated and there will be no more acetic acid left, ethanoic acid left in the buffer, and after that the pH will increase. So this is the fundamental how the pH works or buffer works. Okay, so now we will study how to prepare buffers solution. How to prepare buffer solutions. So I will discuss about the acidic buffer, and similarly you can do for the basic buffer as well. So how to prepare? Suppose my acidic buffer is acetic acid made of acetic acid and sodium acetate. sodium acetate and acetic acid. So this is my acidic buffer. So how to prepare this buffer? So in order to prepare this buffer, what I can do, I can take equal amounts of acetic acid and sodium acetate, and then I can mix them. So I will get this combination of acetic acid and sodium acetate, and my buffer will be produced. So equal amounts of acetic acid and sodium acetate. Secondly, how can I prepare? I can take acetic acid in excess. I can take acetic acid in excess, and then I can take sodium hydroxide, mix it with limited amount of sodium hydroxide. So what will happen? Because my acetic acid is in excess, so it will react with sodium hydroxide and sodium acetate will be formed. So there will be some sodium acetate and there will be some acetic acid. So that will form our buffer again. So suppose I take 200 moles of acetic acid and I take 100 moles of sodium hydroxide. So acetic acid will react with sodium hydroxide to form sodium acetate. So 100 moles of sodium acetate will be formed, and the leftover 100 moles of acetic acid will be there. So we will get an acidic buffer. So we will have sodium acetate 100 and the leftover 100 of acetic acid. What else I can do? I can take the salt of acetic acid this time, excess of CH3CONA. I take excess of this and I mix it with HCl, and HCl is my limited amount. So suppose I take 200 moles of sodium acetate and I take 100 moles of HCl. So again my HCl will react with sodium acetate to form sodium chloride and acetic acid. Sodium chloride won't affect our buffer. So now we will have acetic acid and sodium acetate left over. So again I will get a buffer solution. Similarly, I can create the basic buffer as well. Okay, so now we will study the pH of the buffer, which is given by Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. So this is the name of the scientist, and from this equation we can get the pH of the buffer. So Henderson-Hasselbalch equation for pH of buffer. So according to this equation, the pH of the buffer depends on the pKa of the acid, the concentration of the acid, and the concentration of the conjugate base of the acid. So on these three factors the pH of the buffer depends. So we will see what is the relationship between all these parameters. Let us take an example. This is Ha represents our weak acid and it dissociates partially to give us H plus ion and A negative ion. Now we can write the equilibrium constant for this acid, H plus ion into A negative ion over concentration of Ha. Okay, so this equation can be written as, we can further rearrange this equation, Ka equals to H plus ion concentration multiplied by A negative ion concentration over concentration Ha. Now we take the log of both the sides. Take log of both the sides, we get log log to the base 10 of Ka equals to log H plus ion concentration plus log A negative ion concentration over concentration Ha. Why it is like that? Because we know that log xy, log of x into y is log x plus log y. So this is the formula of the log. Now we multiply this equation by minus sign on both the sides, so we get minus log to the base 10 Ka equals to minus log H plus ion concentration and minus log concentration A negative over concentration Ha. Now tell me, what is minus log Ka and what is minus log H plus ion? So we know that this value is equals to pKa and minus log to the base 10 H plus ion concentration is pH, and the other value remains the same, this one. Okay, so now we can rearrange this equation. We can bring this value log concentration A minus over concentration Ha on the left hand side, and we will get pH equals to pKa plus log concentration A negative over concentration Ha. So this equation is called Henderson-Hasselbalch equation. This is a relationship between pKa of the weak acid and the concentration of the weak acid and the concentration of its conjugate base. So if we know the pK of the acid and the concentrations of weak acid and its conjugate base, we can find the pH of the buffer. Similarly, we can do for the basic buffer. So suppose my basic buffer, for example, ammonium hydroxide and its salt with strong acid, that is ammonium chloride. So we take ammonium hydroxide is our weak base. It will partially dissociate into ammonium ion and OH negative ion. So we can write the equilibrium constant for the base, that will be ammonium ion concentration multiplied by OH negative ion concentration divided by the concentration of weak base ammonium hydroxide. We can rearrange this equation in this form: ammonium ion concentration over concentration of ammonium hydroxide multiplied by OH negative ion concentration. Now if we take log of both sides, we will get log Kb equals to log concentration of ammonium ion divided by concentration of ammonium hydroxide, and log m into m is log m plus log n. Now if we multiply it by minus sign on both the sides, we get minus log to the base 10. So these are all the log to the base 10. So minus log to the base 10 Kb equals to minus log to the base 10 of ammonium ion concentration over concentration of ammonium hydroxide minus log to the base 10 OH negative ion concentration. Okay, tell me, what is minus log to the base 10 Kb and what is minus log to the base 10 OH negative ion concentration? So we know that this value is equals to pKb and this remains the same. Ammonium hydroxide, and this is POH. So we can rearrange this equation, then we will have POH equals to pKb plus log to the base 10 of ammonium ion concentration divided by concentration of ammonium hydroxide. So this is also Henderson-Hasselbalch equation. for basic buffer. If we know the Kb of the base, and if we know the concentrations of the weak base and its and the concentration of its conjugate acid, we can find the pOH of that buffer, and then from pOH we can find the pH of the buffer. pH will be 14 minus pOH.